welcome back to Samvaad. So today we have the third talk of the theme, namely Vistas in Spatio-Temporal modeling. Today's speaker is Professor Shivakumar Malapaka, who will be speaking about studies of 3D MHD turbulent flows at various magnetic Prandtl numbers. Professor Balakrishnan Ashok is the session chair for today's talk. Professor Ashok is currently an associate professor here at IIIT Bangalore. His research falls in the areas of complex systems, nonlinear dynamics, biomechanics, and biology motivated problems, and so on. So without further delay, let me hand over the stage to Professor Ashok to introduce.
Thanks, Professor Nikhil. So today we have, as Professor Nikhil just said, Professor Shivakumar Malapaka, who's going to talk to us on studies of 3D Magnetohydrodynamic turbulent flows at various magnetic Prandtl numbers. Professor Malapaka is currently an assistant professor at the IIIT, and he worked for his PhD at the Max Planck Institute for Plasma Physics at Garching, München, and got his degree from the University of Bayreuth in Germany in 2009. His thesis was on the simulations of three-dimensional magnetohydrodynamic turbulence. He has had extensive postdoctoral experience, including work at the University of Colorado Boulder, UPMC at Paris, the University of Leeds, as well as TFR TCIS at Hyderabad, and the University of Rome, Tor Vergata at Rome. He has various research interests, including principally in three-dimensional simulations of hydrodynamic and magnetohydrodynamic turbulence, simulations of magnetic confinement of plasma, and in-body simulations of for planetary formation. And I'll now hand over the mic to Professor Malapaka so that he can start delivering his talk. Thanks.
Yeah. Thank you very much, Professor Ashok, for the kind introduction. Yeah, sorry for the delay. The delay was from my side. It got into the last minute of preparation. Sorry for that. So here I present my latest work that I have been doing for the past almost 2 years, various simulations and other work on studies of 3D MHD turbulent flows at various magnetic Prandtl numbers. There are a few things to understand in the terminology, which I will introduce as we go on. The turbulent flows in Prandtl numbers and things like 3D MHD. Okay. So before we start, we should understand what we are aiming at. We are aiming at understanding the magnetic fields of the universe at various scales. Okay, it could be the scales with respect to, say, for example, clusters of galaxies, where the scales are billions of kilometers. If I write it in terms of kilometers, these are usually megaparsecs. Okay, that is shown in the bottom left. And we also have Sun, which is about say 6,000 kilometers in radius, 6,000 kilometers in radius, a ball of plasma, and its influence, magnetic influence, is felt all throughout the solar system, hundreds of AU. And especially you can see that is the rightmost top picture, where we can see that the influence of the magnetic fields of the Sun influencing the magnetic fields of the Earth shown there. Also shown here is the magnetic field of the Earth itself, called the geodynamo, shown with this beautiful simulation done, where it shows both the poles, the North Pole and the North Pole field lines and the South Pole field lines shown in blue and say gold. Also, there are some practical applications of understanding the magnetic fields, because if you want to say achieve fusion reaction, which is one of the main aims of the humanity, because that would be sustainable energy source, we need huge magnetic fields. magnetic fields need to be generated, and the plasma need to be confined in devices shown, one of them shown here, with a human sitting in. It is it's in Princeton, one of the tokamaks. This device is called a tokamak, and there people introduce plasma and run with the or accelerate the plasma with using the help of magnetic fields, and allow them to collide the plasma particles, and we try to get fusion power. Currently, the best fusion power that we are getting is for few seconds only, or even less. The recent one month back, there was a paper said that they sustained the fusion reaction for 5 seconds. I think that is the largest ever fusion reaction done. Now, what is all common to all these say systems? Okay, plasma. That is the main component that is present, which is driving all the magnetic fields. This is elementary physics, 12th class. That if you have a charged particle moving, it will generate magnetic field around it, right? The very elementary 12th class physics. That's exactly what we are trying to understand. But not one elementary particle, but millions of elementary particles, which are called plasma, the fourth state of matter, which is almost 99% of the known matter universe. So this is covering, this particular thing covers interstellar medium, the interiors of the stars, to our own atmosphere, ionosphere, and so there is plasma everywhere. So we want to understand the behavior of this plasma when it is moving. So the speciality of plasma is that it looks as much as a fluid. So the governing equations for plasma are both fluid as well as, because I already mentioned it's a charged particle moving, it also generates magnetic fields. So we have to also look for other equations that can say take care of this aspect. So where do we get them? We get them from the Maxwell's equations. So we combine the fluid dynamic equations with the Maxwell's equations and create a field of studies called Magnetohydrodynamics. And so that is the field of the combined field of magnetohydrodynamics. So we have fluid dynamics, which is hydrodynamic turbulence usually, and hydrodynamics, and then comes the Maxwell's equations, which take care of the charged particles and their behavior. So yeah, magnetohydrodynamics. Now the system becomes much more complex, obviously, right? So when you want to solve a number of equations which are nonlinear, because all these systems are completely nonlinear in nature, so they become completely complex, and so we have to understand the behavior more or less in an approximate manner. We cannot get exact answers to any of the problems that that these systems pose. Normally we go to approximations. So what are the equations, as I mentioned, that govern, and what are the assumptions that are made every time to time? So there are many assumptions that are made. So the basic assumptions that are made in the studies I do are that I assume that the plasma is single fluid. Why is this important? Plasma is usually consisting of stripped ions. So there are electrons and the positive part of the ions, positive part of the atoms called ions. So electrons on one side and ions on the other side. So this is because when you heat a gas, that is what happens. So you want to study at least one thing correctly. or in the single fluid approximation, the movement of electrons is too fast. Okay, that is known for ages, and the ions are much slower because of the way they have to carry the whole nucleus along with. So if we study, say, only the idea of electrons, that mostly suffices because that is the fastest moving component of the plasma. So if we can, in principle, study that, or only study ions if we want. So people usually study the electron plasma because the movements in the electrons are faster, and so they may determine the dynamics. However, it may be very interesting that, say, in many places, the electrons may even escape out of the systems. So, like for example, we may not find the electron streams. Okay, they may be coming towards, they may leave the source. So, time to time, this idea of single fluid approximation keeps on, say, modifying. So normally when people are studying single fluid approximation, they don't specify what exactly they want to study, because the parameters inside the systems can be tuned to either electron side of the plasma or the ionic side of the plasma. Okay. So then we assume isotropy. That means everywhere the system looks the same. Okay, and homogeneity. So wherever you go, again the properties of the system are the same. And for the sake of simplicity, I also assume incompressibility in the system. Normally, when you look at a sun or any such system, there is always some compression that is happening. Shock waves and others are associated with such compressions. But once the shock is a short-lived event. So once the shock gets over, the system relaxes, and normally the system stays in that relaxed state. That means in the incompressible state for a longer time than in the compressible state. So it's a fair approximation. So with these assumptions, the parameters that we study are velocity, the parameters that come into the equations are velocity, magnetic field, as shown here. This is the classical Navier-Stokes equation with the additional term, that is the magnetic force term or magnetic field term added here. And this is the advection equation, that is the second order loss. This is a Laplacian. So we have diffusion with respect to the hydrodynamic field. So it is called kinematic viscosity, mu. And then we have the induction equation, which is shown here, which is coupled to the velocity field by the Lorentz force, V cross V. And then we have the magnetic resistivity term, beta, or magnetic diffusivity, and a second order differential, that is the Laplacian in B also, which takes care of the diffusion that happens in the magnetic. We also have a del dot B is equal to 0, which is the classic Maxwell's equation, which says there are no monopoles in the system. We also have the pressure, because when moving fluid exerts pressure, definitely. But what we try to do is we assume that the pressure is a passive scalar in our case. So when we assume pressure to be the passive scalar, if we take a cross product of the first equation, then the pressure term vanishes, as you can see here. And we arrive at what is known as the vorticity equation. So the second equation, the non-dimensionalized equation mentioned here, is called vorticity equation, where it is written in terms of the cross product of the entire equation, and the terms are shifted to the right hand side total. Okay, and del cross B is equal to J, so the del cross B has been replaced by J. Okay, and also the idea of non-dimensionalization that comes into this particular set of equations comes from the fact that we want to use the set of equations to any given system. The previous systems mentioned above in the previous slide. So we have for sun or cluster of galaxies or plasma fusion or Earth's dynamo, whatever may be the system, we want to use the same parameter set. So if we want to use the same equation set, then we have to have a kind of non-dimensionalization of the equations. How do you do this non-dimensionalization of the equations? By defining two terms, L0 and V0. So these L0 and V0 are the characteristic length scale and the velocity of a particular given system. Okay, so if we now use this L0 and V0 and also define say kinematic Reynolds number and magnetic Reynolds number as shown, Re and Rn, as L0 V0 by mu and L0 V0 by eta, we end up with two parameters, mu bar and eta bar, which are now taken care of the non-dimensionalization of these equations. In this set, the magnetic field is expressed in units of alphen speed velocity or alphen velocities. Okay. So the magnetic field is now expressed in alphen velocities. Okay. Now, further, if we have to use these equations and say do what? That's the next question. So we simulate these equations, but where? So we simulate these equations by converting them into the Fourier space. So in the Fourier space, as you can see from the non-dimensionalized equations getting converted into the Fourier space. So the equations that are present to the bottom right of the corner of this slide, which are dou t omega tilde is equal to ik cross bk v cross omega bar tilde and so on, those are called the equations in Fourier space. Okay, the k there represents the wave number. Okay, so the full set of equations shown there are all the wave number, the equations after transformation into Fourier space, and the Fourier variable here is k, and its inverse variable is the length scale, any L, okay, x, y, z, whichever, or root of x square plus y square plus x square, whatever. The length r, it could be r also. Okay. So the tilde term shown here, which is shown, what is the expansion of the tilde term? It is a convolution term shown at the bottom of the rightmost bottom of the set. You can see there. Okay. So that equation d cube k bar b tilde k bar omega b tilde k bar cross omega tilde k minus k is a convolution integral. This integral in general is responsible for the generation of different scales in the system. Okay, how? You can see in the equation shown as f star g or f tilde star g tilde, which is a convolution equation, which is traditionally written as fpg k minus p dq p, which could also be written using a Dirac delta function as f tilde p g tilde q and delta function of k minus p minus q dqp dqq. This additional scale that has come about, which is an intermediate scale which interacts between say the scales p and q, okay, creates every time a new scale. Okay, so the k, and these k scales typically are having what is known as the triadic relation, which means k plus p plus q is equal to 0. These are all vectors, and if you add them, you get a 0. So that is the triangular. So because they form a triangle, they are called triadic interactions, or triadic vectors, and the interactions between them triadic interactions. Okay. Now there is an important other parameter that we are interested in this particular talk, that is PRM, that is the magnetic Prandtl number, which is the ratio of magnetic Reynolds number to the kinematic Reynolds number, Rm by Rn. We'll talk about it little later in the next slides. But before we go from here, this is in general the MHD equations. We are now supposed to understand what is the turbulence part of it. So in general, a general understanding of the hydrodynamic turbulence is that there are, say, there is a large, large scale injection of energy, typically, and the structures you are in the hydrodynamic turbulence are called eddies. That's the traditional usage, okay, of the for the name of for the structures. So there are large scale eddies where usually, traditionally, energy has been injected, and this energy dissipates over time. Okay, during this energy creates turbulence if a critical Reynolds number is overcome, and slowly the turbulence will create smaller and smaller structures, and the energy that was injected gets dissipated, and over much smaller and smaller scales, say where there is completely say heat or radiation that dominate the dissipation, we lose the turbulence. In between these two extremes, that is injection of the energy and the dissipation of the total turbulence, there is a region in space or in scales, in scales which are intermediate in nature, and where the system is completely dependent on the nonlinear term and is independent of either the forcing or the dissipation. And this particular area is typically called the inertia or inertial range, owing to its origins in the hydrodynamic community and closely related to the inertia of the system. Okay, and here the flux of whatever quantity that you are studying, if is a constant, any physical quantity, then it is said to be doing a cascade. Okay, so if a system, as you can see, if you plot a spectrum of the rightmost figure, you get a spectrum of the kind shown in the left bottom figure, that is where you have on the base wave number, and on the say y-axis any quantity, usually in logarithmic scales. So here we show energy. So you see here that the energy is injected in the K force scale that is shown here. That is the highest length scales or the smallest wave number region. Okay, and the curling arrows represent the interactions or the cascading that is happening into the dissipation region. And in the dissipation region, we have a eta, k or k eta it is called, which is sorry, here there is an inconsistency. It should have been k mu, because I use k eta for something else in the letter. Sorry, k mu, which is the Kolmogorov, okay, where the dissipation kicks in. Until then, there is inertial range, and as soon as Kolmogorov scale is reached, you enter the dissipation range. And then we have in the intermittent or intermediate region between the injection scale and the dissipation scale, nonlinear interactions or local interactions. The nonlinear interactions or local interactions are characterized by triangles that are either closely equilateral or extremely scalar. You can see here the extremely elongated scalar triangles indicate nonlinear or non-local interactions, whereas almost equal or equilateral triangles indicate local interaction. And here we also see one say three-dimensional visualization of the structures, and there is a phenomenon of intermittency in turbulence, which is associated with the structures where we don't know yet how, which is a very open problem. Many groups across the world are studying it. We don't know yet how and when, but there is definitely some change in parameters, sudden change, which is why the word intermittency, sudden change in parameters. Those parameters will create or sustain turbulence, create sometimes, many times, and also sustain turbulence. So we also want to understand this intermittency in general. Now coming to the Magnetohydrodynamic turbulence. We said that there is turbulence. Now we want to understand Magnetohydrodynamic turbulence. So typically Magnetohydrodynamic turbulence also shows a similar behavior as we saw in the hydrodynamic turbulence case. So in the center we have this magenta colored plot, wave number versus energy, which is showing exactly the same idea that was presented in the previous slide. That is, we have larger eddies, an intermediate region or inertial range, and a dissipation region where small scales are present. Okay, this typically the case has been that people have been injecting, say, energy or any other physical parameter into the drive range or large eddies and see what happens, and then simulate the system and see what happens to the same as it moves towards the smaller scales. But there is one parameter which was found in which was defined in 1960s called helicity, and especially by Moffat and others. And it started with kinetic helicity, and then magnetic helicity was also found, which is the measure of twist or turns in the field lines, okay, and also linkage between the field lines. So it is defined as it's a scalar, and it is defined as the volume integral of the magnetic vector potential A dot the magnetic field itself over the entire volume. Okay? So this particular quantity, Hm, is called magnetic helicity, and as we can see, it represents some kind of a, because A is del cross, sorry, B is del cross A. Okay, so there is some rotation and twist that this particular quantity is associated with. Okay, so when twist or rotation are associated, with any given structure, naturally topology also comes in. So for example, we can see here that there are two rings. So we try to find out how these two rings are linked together. So we find a linking number, and then if the rotation is in the wrong, the other direction, the linking number cancels. If it is in the same direction, linking number adds up. Okay. So, but what is the speciality of this particular MHD quantity called helicity? It is a conserved quantity in ideal MHD. Ideal MHD would mean that there are no dissipative forces in the system. Okay. And also, there is no forcing to the system. That is what ideal MHD is. And then it goes the other way. That means if every quantity, especially like a quantity like energy, if you inject it into the large scales, it spirals down to the smaller scales. Magnetic helicity, on the other hand, if you inject it in the small scales, would move up and create larger and larger scales. So this idea of creation of larger scales is called inverse cascade. And if inverse spectral transfer, and if the flux is constant in this process, it is called inverse cascade. Okay, it was observed that, as you can see here in the rightmost plot in the middle panel, the initial condition is shown in green. Okay, and the simulation was moved in time, or progressed in time, and you can see that the peak of this quantity, which is in the intermediate stages has been drawn in khaki color, and the final stage drawn in magenta, has moved in space from about 100 to about say k is equal to 4 or 5 in time. So the direction is, say, towards the left. Okay, so this process, okay, is called inverse cascade, and it is believed that inverse cascade will create large scale structures from extremely small scales. Okay, small scales, the initial, here there are two pictures shown. Okay, one with extremely small scales, and next large scales of the mod of B, that is modulus of the magnetic field, absolute of magnetic field. And you can see that the initial state is the initial condition of the system, where it would have, the system has been initialized with extremely small scales, random Gaussian. And as the systems, the simulation time progressed, large scales got created, and you can see the several eddies coming out into the system. Now, is there a necessity that the magnetic helicity should say scale or move towards larger scales? Mathematically, yes. That is because of this particular relation shown here, which is called the detailed balance. Okay, so if the detailed balance in the system has to be achieved, then the triadic interactions should be moving the magnetic helicity to smaller scales rather than the larger scales. Hence, we see that by constraint of the mathematics, as well as its own physical nature, magnetic helicity moves towards larger scales. Now, intermittency, as I mentioned earlier, is an important phenomena we want to understand. This particular topic we will not discuss in this particular talk, but to keep the ideas totally complete, I have put this slide. Okay, so the first ever, at least known documented evidence of the swirls were from Leonardo da Vinci about 500 years ago. He he plotted these he drew this wonderful figure that is where he observed water flowing from a pipe and falling on some rough surface and creating those swirls, and he drew all of them painstakingly, very beautiful. Okay, so here these swirls represent the intermittent nature of the system. Okay, because over time they would die down, and the flow would become smooth after a certain amount of distance. But why were these swirls created? Or how exactly they got created, and how they suddenly passed energy from one scale to another is not very much clearly even now understood. So this particular thing is a very open problem, and people try to understand it using what are known as structure function analysis, that is 2-point correlations, or PDFs, probability density functions, correlation functions, and kurtosis analysis. So there has been several attempts to understand intermittency, but I can say with more or less certainty that the current state of affairs is that it's a big open problem. Okay. So we also have studied intermittency in MHD turbulence previously and understood the behavior of active regions of the sun. This particular cartoon in the rightmost corner bottom was one such thing which helped us understand the behavior of say the active regions of the sun before and after the flow. Now we perform direct numerical simulations to understand whatever we have now just said earlier. So we use the following equations shown here. So here first equation is the vorticity equation. We also have some additional terms here and some additional parameters. This Laplacian to the power n of omega is called hyperviscous hyperviscosity, or introducing of hyperviscosity. So this hyperviscosity is a quantity which is completely numerical in nature. It does not disturb the flow except for a small bottleneck in the close to the dissipation region sometimes, depending on how the initial condition was. But most of the times the hyperdiffusion will aid in cleaning up the inertial range, which is the intermediate range between the dissipation range and the energy injecting range, and it will clean that particular region of any noise. Now, why is that important? Because I forgot to mention in this particular slide that in the intermediate region or intermediate region, or the so-called inertial range, the system has a power law like behavior. So the total energy behaves as k power minus 5/3, and the magnetic helicity behaves differently in different systems. Like for example, in the forced case, it behaves as minus 3.3, and in the decaying case, it behaves as k power minus 3.6. Okay. Now, so then we have this similar setup is there for magnetic field also. That means we are also introducing hyperdiffusivity into magnetic system also. Also, there are these two terms FF, FV and FB, which are adding forcing to the system, and if they are zero, the system is said to be decaying in nature. And also there is a alpha times inverse Laplacian, which is a sinc term, which will say when the system reaches its extreme peak. That means when the magnetic helicity moves, I have shown you here, the peak of the magnetic helicity is moving, as you can see from the khaki curves and the magenta curve, towards the boundary. Okay, so if eventually it hits the boundary, then there will be a back reaction of the system to the system, and again the inertial range gets noisy. So in order to avoid that, we introduce a sinc term which will take away the additional say energy that gets generated into the extremely large scales temporarily, I mean, at every time step, and then keeps the inertial range clean. So it avoids the back reaction, and because it is limited to only the last few say, or it is significant only in the last few k, that is extremely small wave numbers, it does not have any significant influence on the other scales. So it only acts at the boundary of the system. Okay, and we also have an additional say term, and we can also keep many other forcing terms if you want. We can keep a rotating term, we can keep other forcing terms on the RHS. Here we are also talking about, but not the simulations I am not presenting here. We are also having additional forcing term, which actually introduces a large scale magnetic structure, which helical large scale magnetic structure into the system. So where do we use, or where do we simulate these simulations? We simulate these simulations on a periodic grid, cubic periodic grid, that is a box, okay, in a regular cubic grid. And typically what is done is that this cubic side of each side of the cubic grid is say defined in the dimensions of pi, so that it is considered as 2 pi. So that each dimension is called 2 pi, and you break this particular the 2 pi into either whatever number of points you want, that is 512 cube or 1024 cube or 2048 or whatever is your computing power. Based on that, you break the system. Now why is it done so? It is done because in the Fourier transform and inverse Fourier transform, typically this 2 pi constant keeps on coming. So if you make your grid itself 2 pi as the base dimension, then you don't have to worry about always the transformation into one set to other. Okay, Fourier to inverse and inverse to real. Now what is done? We use periodic boundary conditions, that is whatever periodic box you see, it gets replicated all across the universe, if you assume so. And we use a pseudo-spectral method, which is that whenever there is a convolution in the periodic, I mean Fourier domain, you come back into the, you do an inverse transfer, come back into the real domain, and we all know that convolution in any other domain, if converted, becomes a multiplication in the converse domain, P or F or K and X, any such so converse domains. So here we have K and X, okay, or K and R. So the system will be able to so we get simplicity in calculation, because multiplication is much cheaper say application than a convolution by default. So you can convert wherever you have convolution, you can go into the other domain, simply do a multiplication and come back. That is equivalent of doing a convolution. So that's exactly what is done. So we use pseudo-spectral method. the integration scheme at the end of the day is modified leapfrog scheme, which I am not describing here. We use spherical truncation. What is spherical truncation? Spherical truncation is you construct you take little more additional modes than what are necessary for the Fourier analysis, and pump in all the noise, that is numerical noise, that is generated in the necessary modes into those additional modes, and then truncate the system. So that way, spherical de-aliasing takes care of all the modes, and you can use all the available modes. For example, typically, because of the symmetry nature of the Fourier domain, if you work with, say, for example, 512 cube, you have effectively 256 modes available. Okay, minus 256 to plus 256. So now you take a little more than necessary modes, and you can, once you spherically truncate, you have all the 256 modes available for your work, and they will give information about your system. Other forms of say de-aliasing are 2/3 de-aliasing. That means if you have 256, they will use only 256 into 2/3 modes. Okay, so you lose certain modes in that process. Okay, as I already mentioned, we use hyperviscosity, and these systems are usually huge, so we need to parallelize the entire code and use MPI and OpenMP and work on say high performance clusters. I work on 2 clusters. One is in-house, sponsored by the BRMS project that I got, and other is IIIT HPC cluster as a part of my visiting association with IIIT. Okay, now the important quantity we want to study in this particular studies is magnetic Prandtl number. Okay, so what I already defined magnetic Prandtl number in the slide, in the second slide itself. That is PRM is magnetic Reynolds number by kinematic Reynolds number. Okay, so now what is the importance or what is the significance of these simulations, or why are we worried about this idea at all? So earlier in my PhD, I did simulations with PRM is equal to 1. Okay, and usually turbulence is associated with different scales. Okay, we have 3 important scales, namely the Kolmogorov scale, which is L nu, that is, or L eta, L nu, and then the resistive scale associated with the magnetic field, L beta, and then the forcing scale, capital L. Okay, and it has been observed that there are 2 kinds of regimes typically: low Prandtl number regime and the high Prandtl number regime. Now, where am I coming from? So if I look back at the magnetic fields that I introduced in the first slide, these structures or these physical bodies have extremely varying Prandtl numbers. For example, in the ISM, that is Interstellar Medium, the Prandtl number can be as high as 10⁻⁷, whereas in the interior of a planet, the Prandtl number can be as low as 10⁻⁷ or 10⁻⁶. Then there are systems where there is Prandtl number of 10⁻14 also. Okay, and on the extreme side, around 10⁻⁶, 10⁻⁷ systems are known. So, and fusion plasmas come in between. So that is why I actually have shown you in the below geophysical plasmas on the low RM side, high Prandtl number as astrophysical plasmas, and in between I put in the fusion devices, because Fusion devices based on the plasma introduced and many other parameters are known to have Prandtl number, magnetic Prandtl number values ranging from 0.1 to sometimes even 100. Okay, so there are these three scales. That is the Kolmogorov scale, as I already mentioned. There is the hydrodynamic dissipation begins. Okay. Then there is the resistive scale, which is usually associated with the diffusion in the magnetic scale, magnetic fields, and you have your L, the energy induction scales. So typically, it has been observed that in the low Prandtl number region, the largest scale is the energy injection scale, then the resistive scale, and then the Kolmogorov scale. Whereas in the high Prandtl number region, the Kolmogorov scale and the resistive scale switch their places. Now, what is the significance of such systems? So then, okay, there are here you can see. Oh, sorry, I by mistake kept the same same cartoon both in both the places. That's a mistake from myself. So here you can see that if if we are in the so-called say high Prandtl number regions, there is a small scale dynamo that grows, and if we are in the low Prandtl number regions, it is a difficult process. So, it is very difficult to grow magnetic fields, although it is plausible to grow. So, what are the other things that come in? Okay. In the current state of simulations, we are able to achieve, say, magnetic Prandtl number region, magnetic Prandtl numbers of the order of 10 power minus 3 to 10 power 2 or 10 power 3. Okay. In the low Prandtl number regions, the Reynolds numbers that are achieved are 1000 to 2500, and kinetic Reynolds numbers in high Prandtl number regions are only about 800 to 1000, and magnetic Reynolds number is adjusted according to the simulations. Okay. But what I am interested in is, I want to say shift the energy injection scale to extremely small scales. It is neither Kolmogorov scale nor the resistive scale. It is even smaller than both the scales, into extremely small scales in both the decaying as well as say forced cases, and study both low Prandtl number and high Prandtl number simulations. So this is the aim. Okay. Now one can achieve larger and larger resolutions, larger and larger values of high Prandtl number, or go to smaller and smaller low Prandtl number regions. We have very huge computing power. Typically, the computing power I have at hand and the network constraints I have put me or help me only do 512 cube simulations. Okay. Even then, the high Prandtl number simulations are relatively easy, but low Prandtl number simulations are relatively tough because they take longer duration and take a lot of computing time, and you never know whether you have already reached saturation. Okay, so now what are the expected properties of low Prandtl numbers and high Prandtl numbers? If you look at the equations here, okay, so there are important terms. This equation. So there are certain terms, del cross B cross del dot V, and del cross V cross B, B cross del cross B, which gives a B dot del dot B. Okay. So those equations, okay, Okay. Help you understand various phenomena that are happening within the two fluids, sorry, or the two fields, magnetic field and the electric field. So we have in the low Prandtl number region, the magnetic field, it has been observed that there are two equations, right? Vorticity equation and the magnetic field equation. So in that two equations has been observed that B diffuses, that is magnetic field diffuses more rapidly than the vorticity, which means that the field lines, that means the field lines generated by any magnetic any moving charge, okay, are to be stretched in order to get to the creation of larger and larger scales. In order to be able to do that, okay, they need the help of the velocity field. So it is a symbiotic interaction. Okay. And here it was observed that this stretching of the magnetic field lines is achieved through larger eddies, okay, than smaller eddies. And because larger eddies are few in any given system, in a typical system of this kind that I am creating, it will take a very large amount of time before the large eddies get created, and hence the system takes a lot of time to come to say quasi steady state. In this system, the diffusion competes with the advection. So the material derivative, advection means movement of the material itself. That and the diffusion are in competition. So the advection has to overcome the diffusion if it has to move to larger scales. Usually, advection and the stretching of field lines are closely related, because unless the material gets advected, the field lines don't stretch enough, and then you cannot create larger scales. That's the underlying idea. And the structure, because of whatever internal processes that are happening, looks crinkled, and there is very slow growth of magnetic field, because before anything can happen, larger eddies have to be created, and then only it will move the system. So that is the contrast to that. So we have high magnetic Prandtl number regions where the magnetic field diffuses much faster than the vorticity. Okay, so which means that the intermediate scale eddies, that is the Kolmogorov-like scale eddies, will stretch the field lines, stretch and shear the field lines. So when that is done, at intermediate scales, what structures are formed? It forms tubes and ribbon-like structures. Okay? So those are the isosurfaces that get formed. And because now there is no need for large-scale eddies to do this work, even the small-scale eddies will stretch the magnetic field. And because there are a large number of small-scale eddies in a given system anytime, they stretch the magnetic field better and create large-scale magnetic fields. Okay? So magnetic field grows faster, and thin folded like structures in velocity are seen in this particular setup. Now, typically, if we look at the properties of the Earth's core, it is a low Prandtl number system. But what are the various parameters that you associate with this particular system? You can define. Basically, you can measure its radius, inner core radius, outer core radius, angular velocity. All this have been tabulated, and of these, the parameters that are necessarily turbulent parameters are coming in the bottom of it. That is the magnetic Reynolds number, LSSR number, Rossby number, diffusivity. Okay. These numbers are the numbers that tells you that there is, say, a turbulence is happening in the system, and that magnetic field and velocity field are interacting with each other. And we also know, because of the nature of the conducting fluid there, the system is low Prandtl number system. However, there is one more interesting way people have, this is a slight digression, let me say that. Okay. People have studied these kind of systems, the geodynamo and astrophysical dynamos. So what they have done is they did not go to PRM at all. They did not go to the magnetic Prandtl. They tried to understand what are the critical magnetic Reynolds numbers, RM, necessary to sustain the dynamo action. Now, I've been using this word dynamo for a long time. What is dynamo? Dynamo is maintenance and self-organization of a large-scale magnetic field in a system. That is what is dynamo action. So this dynamo action is sustained over large, time scales. Okay, and it has been observed that high Prandtl number regions, high Reynolds number regions are usually astrophysical, and low Reynolds number regions are usually geophysical in nature. And it has also been understood that there is a J cross B term in the equation. Remember, the J cross B term in the vorticity equation, B cross J or J cross B. That term is a term that say links the velocity and the magnetic fields, and it has been observed that it is also the term that will have a back reaction on the velocity. So not only the velocity, as I have been always talking about velocity, it is helping the magnetic field, stretching it and creating larger scales and all. But there is sometimes a back reaction on the velocity field by the magnetic field, and that happens through the J cross B term in that equation. Okay. So, and it has been also observed that in the high Reynolds number, magnetic Reynolds number regions, there is equipartition of energy at every scale, and then the system moves to next scale. So what does that mean? That means that there is equal amount of kinetic energy and magnetic energy at every scale, and if it is not there, they try to achieve that. The scales try to achieve, the system tries to achieve it, and then moves the system to the next scale where there is an imbalance, and again it is achieved, and then there is an imbalance in the next scale, and so on. So that way, the system moves to larger and larger scales or creation of larger and larger structures. This is true to the higher Reynolds number systems. Whereas in the lower Reynolds number systems, the term del cross U cross B, del cross B cross B, the first term in the induction equation, that is highly negligible. Okay. Okay. And so what happens? Diffusion is the dominant phenomenon. Okay. So that is the slight digression from the low magnetic Prandtl number, high Prandtl number work. But this is important to note because usually the low Prandtl number simulations are combined with the ideas of low magnetic Reynolds number, and high magnetic Prandtl number simulations are coupled with the ideas of high magnetic Reynolds number studies. Okay. Now, some of the results. First, I am presenting on the top what I observed at unit Prandtl number in my PhD. I observed inverse cascade of magnetic helicity as time progresses from say initial condition that is in green to through the khaki plots to the final magenta plot. It also was seen in the decaying simulation where the initiation was happening at the intermediate scale and the system moved to larger and larger scales. The same thing was observed in the bottom simulations which belong to the high Prandtl number simulations. Exactly the same situation was observed as it moved from. But what you can clearly observe is that in the say unit Prandtl number simulations, the loss of the way the amount of say energy was lost was much higher, and that is the reason why the amount the x-axis is ranging, sorry, y-axis is ranging from 10 power minus 16 to 10 power minus 9. Whereas here in these simulations, it is only in the 10 power minus 7 to 10 power 0 range. Now, in the decaying simulations, the situation is even better in terms of the high Prandtl number regions because there is larger amount of say energy present in the system. Although why I am stressing this information is I have initiated with the same amount of energy in both the simulations. So this is a natural phenomena that has occurred because of the viscosity that has been put in. Now you see that in the top rightmost corner, a plot of kinetic energy, total energy, and magnetic energy, and similar plot is shown here in the bottom for the high Prandtl number region, high Prandtl number simulations as well. And we see that there is a small amount of equipartition in the unity Prandtl number simulations, but that is not exactly present in the high Prandtl number simulations. And the scale difference between the kinetic energy and the magnetic energy is about say 8 to 9 times in the unit Prandtl number simulations, whereas it is about 10 times or more in the high Prandtl number simulations at the extremely small k or larger scales. So this is the difference that we observe. Now, I am not presenting the low Prandtl number simulations. They more or less have the same idea here. But what I am trying to come to is an important other relation that we found, which we call it as theta, which relates 4 spectral quantities. That is kinetic energy, magnetic energy, kinetic helicity, which is again a twist in the velocity field itself, integral omega dot v over the entire volume dv, and hj, which is called current helicity, which is related to the magnetic helicity by k square h. So this particular quantity called theta was plotted for both decaying simulation as well as forced simulation, and the top plots show the same. The bottom plots are some other quantity which I am not discussing, but I just took those plots from my previous paper, so they came as they are. Sorry for that. So this particular plots, the top plots show that for the value of this gamma here, gamma is equal to 2, the simulations satisfy the relation better. This relation directly links to what is known as magnetic alpha in the nomenclature of the dynamos, where which will generate the large scale magnetic structures. But it has been observed that this particular theta holds better for gamma is equal to 2 even in our simulations. You can see here in both the bottom right and bottom left, but in the middle simulation, which belongs to the decaying simulation, high Prandtl number decaying simulation, it fails. And this trend was also observed in low Prandtl number regions. So somehow the decaying simulations are not adhering to this magnetic alpha, which is not yet clear to me. Why is it happening? Because in the other case that I am going to discuss next, we observed that it is not happening. And we also observed several power laws to the magnetic helicity, magnetic energy, total energy, kinetic helicity, by compensating these quantities as shown here. So I'm showing here one compensation spectrum, that is I'm compensating here magnetic helicity with a k power minus 3.6. You can see that it just fits there exactly, becomes completely flat. That is what exactly compensation means. And it also is true for the forcing case, where it is fitting with minus 3.3. So like that, we fitted for all the quantities mentioned here. And surprisingly, when we plugged in those power laws, that means if I take, say, for example, for magnetic helicity, say k power minus 3.6. Similarly, the power law for k, hk, whatever it came, and so on, and plugged into this relation, all the simulations, right from unit Prandtl number simulations to low, high, force, decay, everything satisfied this relation. Means the power laws are more or less getting satisfied into this particular equation. Okay. Then we also did some time analysis. So what did we do? We plotted what is happening to the system as is. That means we just took the amount of time we calculated, there are energy dissipation and other parameters. We plotted those parameters. So in the magenta color, we see the top magenta plot in the total energy and the kinetic energy, total energy and the magnetic energy. Here in every case, what I am plotting is that the bottom is the black or yellow color represents the decaying case, which takes more time, whereas the magenta color plot on the top is the forced case, which is fast. Now what I did was, I also did some other kind of simulations. What I did is, I took 3 points in the forced simulation, this blue, red and green, and allowed from there the system to decay. Okay, so that is why there are these decaying plots originating from those 3 points for every energy, kinetic or magnetic. It is true for both, say, forced case as well as the for the high Prandtl number case, which is shown on the top, or to the low Prandtl number shown on the bottom. You can see clearly that the low Prandtl number system had to be run for a much larger time. You can see here the time axis shows up to 30. Okay, whereas in the high Prandtl number region, the decaying case ran up to 20 plus, a little over that, and in other cases they ran much shorter times. Whereas low Prandtl number simulations ran in every case for a little longer. Even the forced case. Okay, so what happens if you look at the decaying case more closely? Because it was not visible, it was in the bottom. So we now plot the log-log plot and look at if there is any power law behavior. We found that these systems show a power law behavior. Energy and dissipation, that is total energy and the dissipation, total dissipation, show a power loss of say minus 0.6 and minus 1.655 respectively, which is also true to say, the magnetic field, whereas kinetic energy slightly varies at t power minus 0.8 for the energy, whereas the dissipation follows the same. This is for the low Prandtl number simulations. For high Prandtl number simulations, these power laws were slightly different, but not very much. And they also agreed more or less closely with the unit Prandtl number simulations, which are plotted here. Okay. Now we look at the structures. Now, one important point to note is why were these, say, 3 other sets of simulations done? And the only aim was to do simulations of only forcing and decay. Why were the other sets of simulations done? It was observed that when we look at the structures, in the forcing case, the structures did not develop completely they were only blobbing, but not creating the full 2-dimensional structures that we want to see. So if we remove the forcing, these structures emerged out. This particular idea came in my thesis. So I used the same idea. I looked at the structures again here too in both the cases. It remained the same. So I had to resort to the same kind of simulations. So here I show say the magnetic Prandtl number of unity simulations. These are old simulations. Start with an initial state, and if I remove the forcing at a very large, at the very end of the simulation, and where the magnetic helicity peak is around the smallest scales possible, and allow the system to decay, these huge large-scale structures emerged. Okay. Now, when I look at the system here, when I want to look at the systems that are present here, I'm looking at 4 parameters. Okay, so on the right bottom here is magnetic helicity. So right up is magnetic energy. Right top, left. The top panel is velocity and magnetic helicity, left and right, and bottom is magnetic helicity and vorticity. Okay. So what was the prediction? The prediction was that the structures will be crinkled in nature, and okay, diffusion takes over, and there are lots of fine structures in velocity. So we observe all the same in this particular set of systems. And in the helicity, I'm showing this particular thing because I have some other interest to show you in the next few slides. Okay. Then, if I look at the say high Prandtl number regions, the same quantity is little jumbled here. Magnetic field is in the bottom left. Velocity and vorticity are on the top, and helicity is on the bottom right. So here the structures are, as mentioned, smooth, filamentary in nature. As you can see, that's how the description was. Okay, thin folded structures are seen in high Prandtl number regions or high Prandtl number simulations. So that's exactly what we see in all the cases. These folds are there everywhere, like nets. Okay, so now I observed one very important and interesting feature, and I want to highlight this. in the magnetic high Prandtl number simulations. That is, I observed a helicity wave in the system. You can, if you, that's why I zoomed in and kept this single slide. I have never seen such a helicity wave in any of the systems, and this I don't know if this is to be related to what people call as dynamo waves, or I don't know yet. And here I am showing the decaying simulation for the low Prandtl number regions. And you see here that the structures are crinkled and velocities structures are not fully evolved. And magnetic helicity is a beautiful structure, as you can see. Okay, and this is the third case that I was talking about. That means I stopped the simulation at a certain time in the low Prandtl number simulations and allowed the system to decay. And you see that this is the end of the decaying simulation. This is the end of the third case, and this is the end of the second case in that, in that 3 points that I took from the forcing case and allowed the system to decay. You can see that largest structures are emerging in the extremely, towards the extreme end. That means when I took the simulation and did the simulation and used the decay simulation at this point, or allowed the system to decay at that, from that point, largest scale structures emerged, and second level structures emerged from the red point, and I'm not showing you the blue point. But in the black one here, that means the bottom curve, for that system, the structures are not so big. Okay, which means to get to large scale structures, we may assume that there is a larger amount of energy needed. As you can see from here in this plot, the total energy in the decaying system is only 0.1 or around, whereas in these points, it started at a much larger value and then is starting to decay. So, which means that for formation of extremely large scale structures, initial conditions play a very important role. That's the conclusion I am coming. And other than this, I'm also working with a few MTech students to understand what is known as reconnection. When magnetic fields are generated from small scales to large scales, they reconnect via current sheets and form larger and larger structures. And currently, there is no direct automatic way to identify these structures. We are forced to run through every frame and identify those structures. So if you can automate this process somehow, then it will be very useful to the community. So what we are doing is, we started with a much simpler system, that is helically rotating turbulence, which is shown here. I worked with Prasad Perlikar of TIFR Hyderabad for this, and I had several samples, say starting from very high rotation, minimum helicity, to no rotation, to no helicity, to maximum rotation. Several parameters have been varied, about 8 or 9 such systems are there. So I gave these particular systems to a set of say students, MTech students, and asked them to identify if they can identify a vortex by training their data set. So first set of students, Ishan, Nitesh Singh, Bagel, Palash, Kamle, 3-4 years back, along with this project was along with Professor Shirishara. So we could identify the automatically using convolutional neural networks, the vortex. Then came another set of students, Subhadeep Sahu, Pushpendra Kumar, and one more student, who actually then identified where this vortex is and cropped the vortex, and then identified which way the vortex is rotating and what is its location. Okay, so you can see first they are able to say that the top vortex is rotating anticlockwise, the second one clockwise, and the parameter range, where is it located on x-axis and y-axis. Okay. So this currently we are at this stage of the work, and if we are able to now use the program written to the magnetic fields, there the number of vortexes is much larger. So our aim is to identify first the number of vortexes, and then identify two close by counter rotating vortices, and then see in the perpendicular direction a current sheet. So this has been a slow work in progress, but hopefully some other students will join and take this work forward. And finally, we also are working with some amount of computational topology. I am supposed to be working with Professor Jaya and Professor Amit. I have started some work with Professor Amit. And one student has recently calculated what are known as persistence diagrams. We don't understand these diagrams yet. This is as new as today. Just now, before a few hours before the talk, I received the data. Amit also has not seen these data. I asked the student to just directly give me so that I can show that something of this sort is happening. But we currently don't understand these ideas. But we are also working on this computational topology and try to understand the structures in the first rotating helical turbulence. The ultimate aim is, as I already mentioned, the magnetic helicity is a topological quantity. We want to use, computational topological methods to see if we can get any further insights into this idea of, magnetic helicity, inverse cascade, and reconnections. So, this is my system at our institute. It's called Future. It is a 160 core processors. 160 processors on 2 nodes, 16 processors. Each processor has 10 nodes. It has the following computing performance, about 6 teraflops. Conclusions. Spectral analysis is consistent with the unity Prandtl number simulations. Structures also are consistent with whatever was observed in the literature. There are some surprises in the decaying turbulence with respect to the spectral relation, which we need to understand further. And automatic identification of reconnection and computational topology methods are a work in progress. Thank you very much.
Okay. Thank you very much, Professor Shiva, for a very interesting talk. Are there any questions from the audience? Okay, I have a few. So until someone asks, I just ask a couple of questions that I had.
Yeah.
In your internal intermittency slide, you said there was a non-uniform distribution of the velocity fluctuations, right? Spatially.
Yes.
So the system has no spherical symmetry then?
Why do we need spherical symmetry?
No, because spatial distribution is non-uniform, right? Because typically when you're doing your
simulation, so the information. Oh, okay, let me tell you the idea. So the intermittency is a highly localized phenomenon. Okay, so on the average, the spherical symmetry is always preserved. Okay, but if you look at instances, then there is trouble, because at certain points this is broken. And that is the reason why, that is one of the reasons why intermittency occurs. Nobody knows. But yeah, maybe.
Okay.
It's an instantaneous, breaking of or instability. It is an instability that occurs instantaneously and then settles over a time period. It again settles down.
Okay. So
the average statistics remain consistent.
Okay, so what is the time scale over which this happens?
Currently, we have no clue, sir. Okay. If this was understood, we can crack intermittency.
Okay. I have a few more questions. I'll just wait if someone else has anything to ask. Okay, no messages in the chat, I suppose. No, okay. Okay, I have a few more then. One other question was, in each simulation, the Prandtl number is kept constant, or does it vary?
No, once you define the Prandtl number through a parameter file,
Yeah.
it remains the same. So when you say low Prandtl number simulation, so you take the ratio of these kinematic viscosity and you make the parameters like kinematic viscosity and magnetic diffusivity in such a manner that in one case it is 10 and in other case it is 0.1. That's it.
Okay, so the plasma number density remains constant.
Number density
means okay, well, per volume.
Yeah.
Number per volume. Oh, okay. So, okay, then how does the magnetic turbulence scale as plasma density?
Plasma density does not come into picture here. The reason is that I'm not doing kinematic simulations. If I were doing kinematic simulations, I would have to also look for the plasma density. But because these are a single fluid approximation, so the idea of density as such does not directly come into picture.
Okay. It doesn't show up in the alpha velocity by any chance? Forgotten.
Alpha. So the okay, I have to look at the alpha velocity idea, because what I know for sure is, okay, let me tell you this. Alpha velocity is important if there is cross helicity in the system. Okay, but cross helicity is closely maintained at 10 power minus 10 or even smaller. That means close to 0 throughout the simulation. So when there is no cross helicity coming into picture, it is very difficult to have the idea of say alpha waves itself. However, because our say the equations are non-dimensionalized and the magnetic field is say designate or is determined in alpha speed units. Okay, so we may have to look at them, but alpha waves by themselves may not occur in this particular set of simulations.
No, because you're scaling with by alpha velocity as the unit, right? For velocities.
Yeah, alpha velocity, yes, but
not the wave. Yeah.
Not the wave. That is what I meant.
Okay. One more thing. Okay, one last question. So in galactic structures, you are looking at low Prandtl numbers, or how is it?
No, galaxy will be high. Only the geodynamo kind of systems, and say for example our furnaces, like liquid metal furnaces.
Right.
Okay, they will have low Prandtl number. They are low Prandtl number. Whereas the fusion devices are a strange mix, because their Prandtl number can vary based on the amount of plasma present and the way the system has been initialized from 0.1 to 100. So they may fall anywhere between a low Prandtl number region, or sorry, low Prandtl number simulation, or low Prandtl number system, or a high Prandtl number system. Okay. That is the only known uncertain system to.
Okay.
Whereas definitely in the astrophysical realm, everything is more or less high Prandtl number. Like for example, the Interstellar Medium. Okay, again, if you go to the core of a star, it is different.
Right.
Like that.
Okay, but in terms of turbulence, is it lesser in galactic structures because you have longer filaments?
No. So the L0 and V0 that we talk about, okay, come into picture. Okay. So there are characteristic length scales, characteristic velocities. Okay. So depending on those systems, again, everything that you have seen currently is in non-dimensional time and non-dimensional time basically. So length scales are also non-dimensional. But once you say put in the say let us say galactic scales, okay, then the times also will become huge accordingly. So the turbulence exists for ages because, for example, if you look at this structure, the bottom left structure, that particular structure typically is at a redshift of z equal to 2 or 3, which is how many billions years, right? Maybe 7 or 8 billion years or more, right? So this structure is evolving. It is not a constant structure still, but the rate at which it is evolving is absolutely low. So if you can say take a snapshot and say in human times, you can say this system has relaxed, Taylor relaxation, okay. But in principle, if you say go somehow ahead of time and look at the same system maybe another billion years later, it could have evolved in much larger structures are found. Okay. So that scale and velocity are completely mind-boggling in terms of our own experiences. So characteristic length scales and velocities always determine this particular kind of say turbulence simulations.
Yeah, right. Okay. And that one, the end you showed us an interesting thing about a wave, right? Helicity wave, possibly.
Yeah. I mean, I am assuming, because there was one paper one paper by Professor Steve Tobias, where he for the first time found the dynamo wave.
Right. Okay.
Okay. So I don't know. I'm wondering if it has anything to do with this kind of a say helicity wave. Are they related, or what is my curiosity? I have to send this particular work to him and ask if he finds any correlation, because this particular I have seen several helicities. Okay, so you can see here on the bottom left one kind of helicity. Okay, then there is another helicity structure there on the top right. Okay, none of them show this beautiful wave running through the entire say cross section of the periodic box. I have no clue why is it coming, because I also have few other simulations and I have seen other helicities as well. I looked for this structure in several other simulations. You see here, this is another helicity, magnetic helicity structure. I don't find any wave pattern, exactly that is running through the center of the simulation. There are, say, some indications of up and down, but they are not such a clean way.
Okay, that can't be just because of diffusion, because it's incompressible, right? The fluid.
Yes, it is incompressible, and that is exactly why I want to know what is the reason. But that because no other say system is showing, only the system with where I stopped my simulation in the largest scales and allowed the system to decay, only showed this particular phenomenon.
Okay.
Even the original helicity plot at that point is not looking anywhere close to this.
Okay, sure. Thanks. Any other questions? Then, if not, then I guess we can conclude this session. Okay. Yeah, I guess Nikhil, so we can guess. Yeah. Okay. Thanks a lot. Yeah.
Thank you.
Thanks again, Shiva, for the wonderful.